In this video, we're going to talk about implicit differentiation. Now, so far, we've been taking derivatives of explicit functions, functions where the dependent variable y is defined by the independent variable x. In other words, things that can be written as y equals some function involving x. An implicit function is one where the relationship between the variables is expressed through an equation. Examples include something like this: x squared plus y squared equals 25, or cosine of xy equals x plus y. And we see here that the relationship between the x and the y in both cases is expressed through an equation. So we call these implicit functions. Now, I want you to consider the graph of x squared plus y squared equals 25. The point 3,4 lies on the graph, even though the graph is not that of a function. Okay, so let's look at the graph here. Let's see what that looks like. So here's the graph right here. We can see that the point 3,4 lies on that graph. Now, we know that this is not a function. If you remember back when you first started talking about functions and you talked about things like the domain, which are all the numbers that go into the function, and the range, which are all the numbers that come out of it, you also talked about something called the vertical line test, which said that if any vertical line passes through more than one point, then it's not a function. And we can see that's exactly the case here. I could draw lots of vertical lines here that would go through more than one point. So we're not talking about a function here. We're talking about an implicit function, but not an explicit function. But the point 3,4 is on the graph. There's a tangent line there, and it still makes sense to talk about the slope of that tangent line. So this idea of a derivative, the graphical interpretation of a derivative still makes sense, even though we're not dealing with explicit functions. Okay, so with explicit functions, we are able to write y as a function of x in the form y equals f of x. And we've seen that. We've seen lots of formulas where we have y equals, and then we got some stuff involving x, and we go on to find the derivative of that. Well, with implicit functions, we often cannot do that. However, we're going to continue to think of y as being a function of x, even though we can't explicitly see what that function is. And I'm not going to get into the details of that, but it's okay to do that. It's okay to think of y as being a function of x, even when we're dealing with implicit functions, because we can always restrict the range in such a way that something that's not a function can be defined as a function. But we're not going to worry too much about that. What we're going to do is just say, all right, we're going to think of y as being a function of x. And so when we look at something like x squared plus y squared equals 25, and an implicit function, we're going to kind of think of it as something like this: x squared plus some function here, I don't know what that is, squared equals 25. Now, this isn't very common. We really don't see this type of thing very much at all, and it's not technically exactly right, but it's sort of the way that we're thinking about things here. Now, the point here is that when we write this, we're going to think of y as being a function of x. Now, let's take the derivative of the entire expression with respect to x. And since the y term involves a function within a function, remember, we're thinking of y as being some function of x. So when we see y squared, that's some function of x being thrown into the square. That's a function within a function. And when we have a function within a function, we know that the chain rule kicks in. And so the chain rule says we're going to multiply the derivative of the outside function times the derivative of the inside function. Well, now let's think about that for a second. We got some function of x in here. Y is some function of x. We don't know what it is, but we're thinking of it as a function of x. And that's the inside function. And we're going to multiply down here. The chain rule says we're going to multiply by the derivative of that. Well, we're just going to represent that by dy dx. That's just going to be our dy dx. Or if you want to use the y prime notation, that's fine too. So let's think about this. X squared plus y squared equals 25. We're going to take the derivative of everything up here with respect to x. Take the derivative of x squared with respect to x, you get 2x. take the derivative of y squared with respect to x. You got the outside function which says bring the 2 down, subtract the exponent by 1, so you get a 2y, but the chain rule says multiply by that derivative of the inside function. Multiply by what's on the inside. So 2y times dy dx. And take the derivative of 25 with respect to x and you get 0. So we end up with this right here. Now what we've done is we've really taken an implicit function which defines the relationship between x and y, and we've turned it into something here that defines the relationship between x, y, and dy dx, this slope of the tangent line. So if we solve this equation right here for dy dx, then what we end up with is a formula that tells us what the slope of that tangent line would be. So here if I just subtract 2x from both sides and divide both sides by 2 to get the y, divide both sides by 2y to get the dy dx by itself, then that's going to give us negative x over y as our derivative. Okay, so I know I just did that, but let's sort of work our way through that problem one more time, just sort of see it all come together. I want to find the slope of the tangent line to x squared plus y squared equals 25 at the point 3, 4. I want the slope of that tangent line. So I start with x squared plus y squared equals 25. I'm going to take the derivative of everything here with respect to x. So this would be 2x. Here we've got a function. I'm thinking of y as being a function of x within a function, the square function. So the outside derivative is 2y, and the inside derivative is that one that I don't know. It's the dy dx. And on the right-hand side, I get 0. So if I now subtract 2x from both sides, then I end up with a negative 2x on the right-hand side. Divide both sides by 2y. I get negative x over y. And that gives me a formula for the slope of this tangent line up here. Notice how it's a little different than the explicit functions that we've been doing before, when we use the product rule and the quotient rule and the chain rule and all those things that we did before this lesson. The difference here is that we've got a formula that involves y. Now it's not always going to do that, but oftentimes it will. And so I wanted to do this at the point 3, 4. I need to know what my x and y values are in order to find that derivative. Well, so slope at the point 3, 4, well, that's just going to be dy dx at the point 3, 4, which would be negative, let's see, x is 3 and y is 4. That'd be negative 3/4. And so I've got it. Okay, so these things can get a little bit tricky. The main thing to remember is, well, there's 2 points here. One is, remember that we're pretending like y is a function of x. So anytime you take the derivative of something involving a y, you got to multiply by that derivative of the inside function. The other point is that, okay, I'm using x's and y's here, but really, remember, sometimes we use other variables. And so we just have to make sure we know which one is the independent variable and which one is the dependent variable. And usually that's going to be given to you as part of the problem. All right, I want to find the derivative of y to the 4th minus 4y squared equals x to the 4th minus 5x squared. I want to find the derivative here. Okay, I see I've got an implicit function. I can see from the graph that this is obviously not a function in the traditional sense. It wouldn't pass the vertical line test. So when I find the derivative here, I'm going to want to find dy dx. All right, so how do we do it? Well, let's see. We're going to go through and we're going to take the derivative of everything up here with respect to x. So I'll start with the first term, y to the 4th. Well, I can do that. That's going to be 4y cubed. But because that was a y term, I have to remember I'm going to multiply by dy dx. All right, looks like with negative 4y squared, I can do that derivative, negative 8y. But because that was a y term, I'm going to multiply by dy dx. On the right-hand side, the derivative of x to the fourth, that's pretty straightforward, 4x cubed. And the derivative of 5x squared is going to be 10x. All right. And so I've written down an expression now that is giving a relationship between the x values, the y values, and the slope of the tangent line, which I'm representing by dy dx. I could have written y prime there just as easily. It may have been a little bit simpler, actually. But I've got this expression here. Now what I want to do is I want to solve it for dy dx. I'm going to try to get dy dx by itself on one side of the equal sign. Looks like I could factor a dy dx out of both of these terms right here, which would give me 4y cubed minus 8y times dy dx over there. On the right-hand side, I've got 4x cubed minus 10x. Okay. Let's divide both sides by this right here, so I get dy dx is equal to 4x cubed minus 10x over 4y cubed minus 8y. All right, so I've got an expression here. That's okay. I could clean this up a little bit. If I factor a 2 out of the top, then I get 2 times 2x cubed minus 5x, and 2 times 2y cubed minus 4y. Make sure I did that right. Yeah, that looks okay. And then those 2's could cancel out. And that would just leave me with 2x cubed minus 5x over 2y cubed minus 4y, and that's my derivative. Okay, so these things can get a little more complicated. Let's look at this one right here. I want to find the derivative. Derivative of 3x y squared equals 3x plus y. Now, okay, fine. I've got this right here. Now let's see. 3x times y squared. Now, what you want to notice here is, remember, we're thinking of y as being some function of x. So when I've got 3x times that, really what I'm doing here is I'm multiplying two functions. And remember, we have a rule that we use when we have the product of two functions. That would be the product rule. So I'm going to call this part right here, I'm going to call this part here u, and the y squared would be v. And when I go in and I find the derivative, well, I got to remember I've got u prime v plus u v prime. All right, so the derivative of u, so that would be the derivative of 3x. Looks like that would give me 3. V is y squared. Now notice I'm not taking the derivative there. I'm just writing v down. I'm just writing down y squared. Plus u, which is 3x, times v prime. Now I'm taking the derivative of y squared. So now I've got to think about, this implicit differentiation stuff. I got to think about, multiplying by the derivative of that inside function. So let's see, y squared, I would get 2y, but then I'm going to multiply by the derivative on the inside, which I'm just going to represent by y prime. Okay, or I could write dy dx if I want to. On the right-hand side, the derivative of 3x would be 3. The derivative of y, well, that's just going to be y prime. And so I'm just going to solve this thing for y prime now. Let's see here. I'm going to take the 3y squared and bring it to that side of the equal sign. I'm going to take this y prime, I'm going to bring it over to the left-hand side. So it looks like what I've got is I've got this one left over here. Okay, so that's going to give me 6xy. And let's see, so I'm sorry, 6xy times y prime. This y prime comes over, so it becomes minus y prime. On the right-hand side, I've got a 3 over there, and I got a 3y squared that's going over. It becomes negative. Okay, I'm going to factor out a y prime right here. So I get y prime times 6xy minus 1. And on the right-hand side, I've got, let's see, well, let me factor out a 3 here. I got 1 minus y squared. And so let's see what happens here. If I divide both sides by 6xy minus 1, I'm left with just y prime on the left-hand side. And so it looks like that would give me 3 times 1 minus y squared over 6xy minus 1. And so I found my derivative. All right, let's look at another example here. I've got 2x plus y squared, all of that cubed is equal to 1. Okay, so I'm trying to find the derivative here. Now, what I notice is I've got some kind of a function here inside of a function, right? The inside function would be 2x plus y squared, and the outside function would be raised to the third power. So when I find the derivative here, I'm going to have to do the chain rule. That's going to give me derivative of the outside. So we bring the 3 out in front, subtract the exponent by 1, and then we multiply by the derivative of the inside. Okay, so now I'm going to multiply here by the derivative inside here. Now let's think about this. Okay, so the derivative in here. Now the derivative of 2x with respect to x is just going to give me a 2. The derivative of y squared, okay, so I've got to think chain rule here again, right? This is the implicit differentiation stuff. I'm thinking of y as being a function of x. So it looks like that's going to give me 2y times the derivative of the inside, which is going to be y prime. And on the right-hand side, the derivative of 1 just gives me a 0. Okay. So I've got this right here. Now let's see. It looks like what we've got here is we've got an expression here that is squared times 2 plus 2y times y prime. You know, if I go in here and say that assume that x and y aren't both 0, assume that this thing right here is not 0, then what I know is that this is always just going to be some number over here. And if I divide both sides by that, then I'm going to get 0 on the right-hand side, and this one over here would cancel out. Okay, so I just had to kind of say, oh, well, okay, let's assume x and y are not equal to 0, and if they are, then I'm gonna run into some problems anyway. So let's see here. Let's assume xy is not 0, 0. And what that means is that we could divide both sides by all of this over here. All right, so if we divide both sides by this is gone, and on the right-hand side we still have 0. So we got 2 plus 2y y prime equals 0. And let's see, so that would give me 2y y prime equals negative 2. And so y prime is equal to negative 2 over 2y, which is going to give me a negative 1 over y. And so I found my implicit derivative right here. Okay, so that's implicit differentiation. I hope this video has been helpful.